So Abrami is not about damage mechanics. Abrami, you might have read in phase transformation MM307. So that is about precipitation. Okay. And I left you with the thought that whether that model can be used for damage also. So what Abrami model is saying that if you have from alpha to beta transformation, okay, so this can be 100% transformation from austenite to ferrite, or you can have precipitation. Okay, so you can have alpha 2 alpha plus some carbide. Okay, so preferentially they will grow at high energy spots, so they will nucleate at the grain boundary, but nothing is stopping them from nucleating also inside the grain where you have high energy areas like twin boundaries, twist boundaries, or the barriers to the dislocation. Okay, so you will have some nucleation inside and you will have some nucleation on the grain boundary, and then they will grow, and they will grow via diffusion, right? So if in this case M is chromium, then chromium will diffuse from the grain or through the grain boundary. So diffusion is fastest on grain boundary, right? Because they don't need a vacant site next to them. And you also have bulk diffusion, you have grain boundary diffusion, and you have pipe diffusion, which happens from the core of the dislocation. Okay, so if you have an extra half plane, then here you have some space. Okay, so from that space, interstitials of course can go, substitutional can also pass through this. Okay, and what happens in ductile damage is that you have nucleation of voids, and these voids are first nucleating and then they grow, and when they grow there are other nucleations also. So this part is same, this picture is same as what is happening in precipitation. You have nucleation of precipitates, you have nucleation of voids. You have growth of precipitates, you have growth of void. While you have growth of precipitates, you have more nucleation of precipitates, right? Same thing is happening there also. So when you have growth of void, new voids are also nucleating. Okay, and then there is a void coalescence. So two voids will grow to a very large size, and then the material which is intact between them acts as a tensile sample. Okay, and then it breaks at UTS, and then these two will become one bigger void. Okay, this part is not happening in precipitation. Okay, so we don't have two precipitates which are growing and joining the two. That is not happening, because when they will grow, so suppose you have two adjacent precipitates of Cr23C6. Okay, so the atoms which are needed for formation of this precipitates are coming from all directions. Chromium is traveling from all directions, carbon is diffusing from all directions, but the highest probability of diffusion, so depletion of the solute, is here. Whatever chromium or carbon is there, that has a possibility to go in either of the precipitates. So more depletion will be happening in between them, and then there will be a zone where almost so much depletion has happened that they cannot join anymore. There will be no growth, right? Which is not the case with voids. Two voids grown, together will, so the material will stretch and they will join together. So coalescence part is missing in Avrami's case, in the case of precipitation. Okay. Even when you have complete alpha to beta transformation, then what will happen? Then the two grown areas will join together, but they will not coalesce because they will have a boundary between them. And that will be the new grain boundary. Right? So suppose austenite is transforming to ferrite. So you had austenite and then you have nucleation of new ferrite phases and they are growing. Right? So each of these will have different orientation because they had no relation between each other when they were growing. So when they join, they will have a mismatch in orientation. So you will have a boundary between two transformed alpha phase, right? And that boundary will not go. But in case of void, the boundary will break and they will become one. So this is missing in the precipitation or solid to solid transformation. So the extended volume concept, which I discussed in the last class, which Avrami uses, there were some errors. Okay. So one error was that they could not exclude the nucleation of new product phase inside already transformed region. That part was not there in the maths of that model. Okay. So the volume transformed in Avrami case was the volume which is growing. So G cube into T minus tau whole cube, and this multiplied by n dot dV, right? So what was n dot? So n was volume into nucleation rate into what, for whatever time it is happening. Okay, so that will come here. So you will have n dot V beta. So this was dV beta, which is the transformed region in Avrami. Okay, this you have read before. So this is written with a superscript of E because this volume is more than what really transforms. Okay, and this is called extended volume because you are not taking care of the new nucleation which is also happening in the transformed region. So we are not subtracting that volume. We must subtract this volume, right, where the nucleation has happened. That we are not doing. And secondly, we are not stopping the growth of two transformed region into each other. That is also not taken care of in the equation. Okay. So the phenomena is, until growth of voids, the phenomena of solid to solid transformation or precipitation. Actually, precipitation is more closer to the phenomena of ductile damage until you have growth of voids happening. So as long as that is happening, that is exactly same. The mathematics, the kinetics is exactly same in both cases. It starts differing when you have coalescence happening in void. Okay. So if you can take care of, if you can, and the other thing with Avrami is that the total volume is constant. Okay, so whatever alpha is transforming to beta, volume will not change. It should. In reality, it should. Because density of the parent phase will be different from the product phase. But to simplify the model, that thing is assumed that there is no change in density. Okay. In case of ductile damage, you will have change in volume. because the voids which are forming is extra volume. It is not forming because of the diffusion of the elements. Nothing is diffusing there. It's a decohesion and an extra volume which is empty is coming in picture. Okay, so you will have an increase in volume, and if you could take care of in this formulation, if you could take care of the coalescence and increment in volume, then this must and can define the ductile damage as well. Okay, but it is not done so far. So it remains as a thought that it can be done. Okay, so there are different ways of defining the ductile damage, and what we have explained, so we have explained about damage parameter omega and kinetics of omega I to omega f. Okay, so that you can very crudely take a formulation which comes from Avrami equation. So you can have, so dV by V, which is f in case of Avrami, is 1 minus kT to the power 4, or there is an exponential here, right? So this is time based, this is a kinetic model, and in case of ductile damage, it's a strain based model. So all the things, the initiation of void, the growth of void is defined by hydrostatic strain or volumetric strain, and nucleation of void is triggered by the shear strain. Okay, so by replacing similar things, so you replace time in nucleation definition, instead of time you find an equivalent of plastic strain rate, right? You can simply try, not necessarily it will be the truth, but you can try. Instead of writing this, you can try the change in equivalent plastic strain. Okay, and in growth you will have to replace time with the volumetric strain, because growth happens because of hydrostatic stresses that appears in the form of hydrostatic strain, volumetric strain. Okay, so when we try to simulate damage using finite element analysis, then all those formulas are pretty simple, that you initiate this, then you follow some equation which tells you to go from omega I to omega f, and when omega f reaches a critical value, then you write in your code that the element should now be removed from the analysis. So element number whatever should be removed, and continuity should be maintained between surrounding elements. Okay, ऐसा नहीं कि नीचे का एक brick निकाला पूरा घर गिर गया, वैसा नहीं करना है. One element is deleted and then you have to maintain a boundary. Okay, so more or less you can take care of damage in this way, but all these are dependent on certain phenomena. So for example, if you change strain rate, not only the stress strain curve changes, but with the strain rate damage will also change. Okay, so if I have a tensile specimen and this is the gauge length, then where do you think the damage will initiate first?
Center.
Why?
Stresses are maximum there.
Why stresses are maximum there? So if I have uniaxial loading, then I have sigma 1, sigma yy is equal to sigma 1, which is the principal stress, and I don't have stresses in other directions. I don't have sigma 2, so sigma 2 is 0, sigma 3 is 0. If I have plane strain condition, then I will have sigma 3 is equal to mu into sigma 1 plus sigma 2, so basically this. Okay, So in both cases, the maximum shear is going to be between sigma 1 and the minimum principal stress, which is any of these. So it is going to be something like this. So if it's a brittle material, it will break, it might break in the shear direction. But if it is very brittle, then it will break flat from the center. Why at the center? Because you have highest constraint at the center. What does constraint means? What is the meaning of constraint? Constraint का क्या मतलब होता है? बताओ?
वहाँ पे ऑप्शन नहीं होता शायद.
Exactly. So you have limited option. So you have moderate constraint. An extreme constraint, that means you don't have any option. You don't have any choice. Okay. So टूटना इसकी नियति है. यहाँ पे जो भी material. Because actually it has a lot of options. It can go in any direction. But the call from all the directions are same. Because it is exactly at the center. Okay. So it's not that it will randomly decide where I will go. It will have to break. It will have to break the bonds there. Okay. And that will not happen from a continuum to a discontinuous. There has to be damage. So void and all those things will happen. And gradually this phenomena of breaking will occur. Okay. So if you have different constraint, then the damage kinetics is going to change. If I apply the force very fast on this tensile sample, then the damage is going to initiate earlier in comparison to the slow case. Okay. If I pull it very fast, or instead of pulling, you can also imagine that if you throw a stone, a pebble on the wall, how much indent that is going to make, and if you hit it with a bullet, how much indent that is going to make. Okay. So if I keep on continuous increment, I have a wall and I have an indenter, and I continuously slowly push it in the wall, then the material gets time to accommodate the strain and deform. Okay. If you remember MM302, which is a curse, is that the strain rate is a function of the dislocation density. Okay. So you have rho and Berger vector and velocity of dislocation. Okay. So if the strain rate increases, dislocation will have to move faster, right? And one of the things has to go down to make the strain rate constant. So either the dislocation density will decrease or the velocity will decrease, right? So if with increase in strain rate, dislocation density cannot decrease unless you provide thermal energy so that there can be annihilation, there can be, so two dislocations will merge together and vanish. Okay. But there are no other ways of decreasing dislocation density from the point wherever you began to deform the material, unless you heat it, unless there is a recovery, there is a recrystallization. If those things are not happening, dislocation density will not decrease. So that cannot decrease. So what will decrease? Dislocation velocity will decrease. Right? Berger vector you cannot change. So you will not have enough time for the plastic deformation to occur. So the amount of total strain a material can take at any given strain rate is going to be less if you increase the strain rate. It cannot accommodate that much amount of strain, and that will cause resistance. So strength will increase. Okay. So, and the similar phenomena can happen if you decrease the temperature. By cooling it faster or heating it faster or applying deformation with a high strain rate, meaning in less time you are providing more deformation. Okay. So that is not allowing time to the material so that it can accommodate the amount of strain it could. If you cool down, then again you are limiting the accommodation of plastic strain. Because if you cool down, then one phenomena which can happen is that the dislocations will have less active slip systems in certain cases. And what are those active slip systems? So for example, FCC, active slip systems are 111 plane, 110 direction. Okay. So per unit cell you have 12 such combinations, so you have 12 slip systems, and all of them are equally stronger. Okay, because on all the 111 plane you have same amount of atoms. Okay. In BCC you have different slip systems. Slip planes are different, slip direction more or less remains the same, but you have different slip planes. And how they become active at different temperature and why they become active at different temperature. In FCC that will not happen. In HCP sometimes it happens, in zirconium it can. So why in FCC the slip systems will not change with in BCC how the slip system changes or increases, the number increases with temperature. Why? Why does that happen? You have stopped asking questions to yourself. You're probably asking questions that your pointer है कि क्या है, but you are not asking these questions. किसी ने बोल दिया slip system increase होगा with increase in temperature. Then now you tell me why.
उसकी पैकिंग की वजह से
Packing change हो जाएगी. Atomic packing fraction on a plane, will it change with temperature? Okay. क्या होगा? बताओ क्या होगा? Why 111 is a slip plane in FCC?
it has maximum number of atoms, like
Yes. Yes. Okay. So suppose you have 4 different planes and all of them have different atomic packing fractions. So one has maximum atomic packing fraction, let us say 60%. The second plane has 50, third has 40, and fourth has 30. Okay. In a crystal, you have such planes which have different packing fractions. You can have infinite amount of planes, right? But those which have packing fractions will be having some atoms on it. You can have planes where there are no atoms, right? In a simple cubic. So if this is, and you can have infinite amount of planes. So if this is a simple cubic, that means you have atoms only at the corners, right? So if I take this plane, I have no atom on it. Okay. So only those planes will have some packing fraction which have some atoms on it, and those are of importance. So we really need to not need to calculate all the infinite amount of planes. So there are, let us say, 4 planes, and all of them has certain atomic packing fraction. Why the maximum packing fraction plane will be the slip plane? Because on that plane, if you want to move the atoms gradually, step by step, like an extra half plane moves, then you have a lot of atoms on it. So the step will be lesser. Okay, the one step, the Berger vector, which it has to complete so that it goes to the next equilibrium atomic site, that is the smaller. So less distance, less energy barrier, so dislocation can move easily. Is it okay? In this case, it is larger, so all the dislocations will be moving on that slip system. Whatever dislocation can form on that slip system. When the temperature increases, then the energy barrier will decrease because the vibration of the atom will increase, the thermal energy of the atoms will increase, it will be making longer jumps in every direction, right? So now the atoms have the ability to jump a longer distance, and that is why even lesser packed planes, on there also you can have slipping. So this is why with change in temperature you will have more number of slip systems getting activated. This will not happen in FCC because there is no plane which has more packing fraction than 111. उससे ज़्यादा हो ही नहीं सकता packing fraction. Okay. So the damage will be a function. It will be a function of strain rate and temperature. Okay. And also constraint. So how do we define constraint? That we will not discuss. We can define constraint in various ways. So constraint is basically the extent of hydrostatic stress you have. That is constraint. हर तरफ से बुलावा जो आ रहा है वो कितना है, कितना ज़्यादा है per unit shear strain. Okay. So in order to find out how the damage changes, we have discussed that experimentally you can do resistivity measurement. You can cut a tensile sample at different sections and then you can look at it under SEM and find out how much damage has happened. Okay, and then you need to change the constraint and see how the damage changes. One tensile sample, I deform it until necking, then I cut it. Okay, I can break it also. So I break it into two pieces and then I just remove a little bit from the top and find out how much void is there, area fraction of that, assuming that 2D is equal to 3D. So I will find out the volume fraction at which it breaks and then I cut it like this, and in this direction my strain is changing. I have more strain here, less there, less there, less there, and elastic there. So I can find out the void volume fraction with a change in strain. So as a function of strain I can find out. Okay. So then I know my damage kinetics, how it goes from Wi to Wf as a function of strain. But this kinetics, whatever variation you get, will change if you change the constraint. Okay. And in order to check that, you impose, you make different type of tensile sample. So you make notched tensile sample. Okay. And you make notches of different radius, because this tensile sample has a notch radius of infinity, isn't it? So then I gradually go to different values of notch tip root radius, and those will create constraint, a constant constraint in this area. But now the problem is that you can't get this variation too much. That you cannot get because this area is very small. You don't need to. Okay, you can just take what is the value of final void volume fraction or WF, omega F, for fracture strain, and then you calculate for different concentrations, so different constraint values, and then you have a relation with constraint of damage. The third thing would be to change it with temperature, and including all those, you can then put the information in finite element analysis, and then you can simulate the damage. Okay. So the last thing which I can discuss today is what I have been avoiding, but it's a very simple topic. So I want to find out the function. I have a function. Let us say the function is y is equal to sine of x, or some function. I don't need to write it. So let us say this is the function. Okay? And I want to find the value of this function at a different time frame. Okay? So I want to find out the value at n plus 1, and I have the value of y at n. So how can I find it out? I have the value of yn, so that means the value of function at time is equal to n. Okay? I want to find out the value of the function at time is equal to n plus 1. How can I do it?
It is dependent on time. You can put the value of n as n plus 1.
So tell me the expression. Yn plus 1 will be equal to what?
If the initial position is known,
So you have reached n from different values. So you have crossed n minus 1, n minus 2, and so on. So how will you find out y is equal to n plus 1? Oh, sorry, y at n plus 1. How will you find out? बोलो.
so function y is equal to sin x ही है.
Function कुछ भी ले लो, log x ले लो, sin square x ले लो, कुछ भी ले लो. It doesn't matter. Whatever it is. Sin x है तो बहुत simple हो गया फिर. That is known.
Time period से आ गया.
Who cares? That is known. बोलो कैसे निकालो बोलो. तुम लोग कोडिंग करते हैं
क्या?
हाँ?
n है क्या मतलब?
n टाइम है. टाइम का वैल्यू n था तो वो वैल्यू था फंक्शन का. अभी टाइम का वैल्यू n प्लस 1 है तो क्या होगा फंक्शन का वैल्यू? बहुत सिंपल है.
सर रिकर्शन यूज कर सकते हो. लाइक इनिशियल हमें बेस केस पता है कि एट t इज इक्वल टू 0 यहाँ पे थे, फिर t इज इक्वल टू n माइनस 2 पे यहाँ थे, फिर t मतलब t इज इक्वल टू 1 पे यहाँ थे, डॉट 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 t इज इक्वल टू n माइनस 1 थे, फिर n. तो उसके बाद में फिर उसी को हम स्टोर करते करते वही इक्वेशन को फॉलो करके n प्लस 1 भी आ जाएगा.
वही तो मैं पूछ रहा हूँ कैसे आएगा.
तो
कौन सा इक्वेशन फॉलो करके आएगा? मैं तो कह रहा हूँ तुम्हारे पास सारी वैल्यू है. yn minus 1 है, yn minus 2 है.
ऐड कर देंगे
किसको ऐड करोगे बताओ? yn में किसको ऐड करूँ मैं?
कुछ कर.
हाँ? अरे ये आधा बोल के चुप मत हो जाया करो. क्या ऐड करूँ? सोच रहे हो? सोचो. ये भगवान.
y of n plus 1 is equal to yn plus function.
नहीं इतना वेग नहीं. फंक्शन ऑफ अलादीन. फंक्शन ऑफ व्हाट? अरे क्या कर रहे हो तुम?
Time period of function is 1. It is equal.
So delta t is 0. अगर डेल्टा टी जीरो है तब तो मैं अपना टाइम वेस्ट कर रहा हूँ ना y is equal to n plus 1 so that is yn is equal to yn that we have proven wow
Plus some constant.
huh
Plus some constant.
what does this mean what does this mean it means yn plus 2 will be yn plus 1 plus c or are you saying c will also change
So then the function should be linear, no? If c is
अब
constant.
तो तुम्हारा लाइन पे इतना सब बोल दिया बताओ कैसे क्या लिखूं यहाँ पे बताओ वो बताओ
A derivative
X
power n y.
yes yes
Derivative of n.
derivative of y so y dash into what or just that just y dash
तो फिर सारे ऐड करने पड़ेंगे डबल डैश
तुम सोचो अभी और टाइम दो y dash plus क्या y dash is the differentiation with respect to what
With respect to time.
with respect to time so unit match करा के बताओ क्या होगा ये तो बड़ा सिंपल हो गया फिर
into delta t.
yes
Delta t.
yes तो बाबा स्कूल में आ गया okay this is very simple no now you have arrived at this
Yes.
by doing a lot of digging हाँ क्या हो रहा है ये IIT में okay so now what are the options I have it will only be a constant when you are taking equal value of interval so delta t is constant and the other meaning is that derivative is not changing okay so this is fine so where should I take this derivative y dash where should I take it so if I plot y versus time and that has this kind of solution and then this is n this is n plus 1 okay and then you have of course n minus 1 n minus 2 and so on where should I take the derivative y dash where
Average of this value.
what
And
average देखो y is equal to sin x so dy by dt will be so sin t कर लो so dy by dt will be
cost t.
cos t में t का क्या वैल्यू डालूंगा मैं एरिया
Integration.
तुम मत सोचो तुम छोड़ ही दो सोचना you stop doing it now area is not the value of the function area is y dot dt that will be area we are not doing that are we are
वाई डैश निकाल के फिर ये
correct है इतना बड़ा एरिया निकालोगे तुम what slope is that giving why have you written y dash into delta t because that is the rate of change of y with respect to time okay if you want to hit this point you want to get this slope only then you will hit that point right you have infinite possibilities of taking any slope you take area or whatever okay so you can take so y dash is cos t and this t now you have to put so t you can put n minus 1 n minus 2 if you put n minus 2 you go in this direction n minus 1 you go in this direction n you go in this direction n plus 1 you go in that direction okay and this is a function where you don't really know where the function is going to be So one possibility is that you take the derivative at the point where you have all the values. So at the time t is equal to n, because that's the previous best value you have. Okay? And if that is the case, then this becomes y is equal to y dash at n into delta t, which is simply Tn plus 1 minus Tn, not necessarily it is 1. Okay, the absolute value of time can be anything else. So n are the points. You are taking different points. Those points can be differently located. Okay. So in this case, if I have to find out yn plus 1 like this, then I don't really have to do anything, because all the values I have. But if I decide to take a derivative at n plus 1, so if I say that I will find out my y is equal to n plus 1 as yn, the previous value, plus y dash at n plus 1, because n plus 1 is the point. That point I know the value of t there, but I don't know the value of y dash there. Okay? So if I choose to do this, then I have a differential equation to solve. If I choose to do this, I don't have to solve anything. I have all the values. Okay? So this approach is called explicit. And that one is called? So explicit analysis has no problem of convergence. None. Okay? Because there is no convergence check. Okay? You are taking the next value based on the slope at the previous value. You don't really know where you are going. You don't know. The curve might be somewhere else and you might be going in some other direction. So then you have to minimize the error. So the best way to do it is take the steps as closer as possible. Make the difference between n plus 1 and n very, 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 very small. Okay? So when we do explicit analysis, and this is needed when we solve velocity types of equations. Okay? So when we have inertial effects, then instead of having strain energy density, so strain energy and the external forces into displacement, so the work done, that you equalize and you get Ku is equal to F, and that is what you solve. Okay? But if you have inertial effect, if you have acceleration, then you have mass also in it, and you are solving Newtonian forces also. Okay? So you not only have strain energy plus external forces, internal forces, you also have external forces, which are coming because of the acceleration. Okay? So there you need to find out double derivative of displacement, which will be acceleration. Then you need to find out velocity, and displacement you have to find out. So there you will need to have two options, either explicit or implicit, and maximum people use explicit because in those cases you need to do things faster. So explicit is a very fast algorithm. You know why? क्योंकि उधर कुछ problem है ही नहीं. Okay? Implicit is not that fast, but it has higher accuracy. It will never diverge from the solution too much. Explicit has a tendency to diverge a lot. Okay? So you need to define, you cannot make the difference between Tn plus 1 and Tn very, very small. If you do that, then also you are increasing your computation time. Okay? So you have to stop somewhere. You can't make the difference 10 to the power minus 18. Okay? So you need to have a good approximation of how much delta t should I have, so that I'm not away from accuracy, my error is not too much. Okay, so if you, for instance, do a damage simulation of a tensile specimen using an explicit analysis and an implicit analysis, you can also do explicit analysis where you don't have relay acceleration. Okay, that you can do, but you have to trick it. You have to trick the simulation. Okay, because if you assign very less mass and you say that by defining very less value of mass I can do explicit, then you will have a lot of oscillations, because very less mass with inertial effect and acceleration will cause oscillation in your material. It will start vibrating. So then you need to add dampening effect and all those. So there are some tricks by which you can also do explicit analysis for those conditions where you do really implicit, works well. Okay, and if you compare the results of implicit and explicit, in explicit, for instance, if you just plot the stress strain diagram which you get from explicit and implicit, and if you plot it, then in explicit you will have a lot of waviness, and implicit will be very smooth. Okay, so we'll discuss a little bit more on this implicit explicit tomorrow in the tomorrow's class, and last two class you can prepare for your exam. Okay, or if you want, we can have a class where you can clear your doubts. Okay.